fill the next part of the objective in part 2. At the end of this video, you will be able to construct and test a synchronous decade counter. Let us collect the tools, equipment and materials required to do this practical. Digital trainer kit IC74LS90, decade counter IC74LS47, 7-segment driver, common anode 7-segment LED display, resistors 220 ohm 7 numbers, connecting wires, magnifying lens. Let us first look into the pin details of IC74LS90. IC74LS90 is a synchronous decade counter and it's part of the TTL transistor logic family. The IC74LS90 is a synchronous counter that can count in binary coded decimal BCD. It's commonly used in digital electronics for counting applications. The IC74LS90 typically comes in 14-pin dual inline package DIP. The pins are numbered as follows. Pin 1 clock input to CLKB. Pin 2 reset input 1 R1. Pin 3 reset input 2 R2. Pin 4 no connection NC. Pin 5 power supply plus 5 volt VCC. Pin 6 set input 1 S1. Pin 7 set input to S2. Pin 8 BCD output QC. Pin 9 BCD output QB. Pin 10 ground GND. Pin 11 BCD output QD. Pin 12 BCD output QA. Pin 13 no connection. Pin 14 clock input 1 CLKA. Let us first look into the pin details of 7-segment driver IC74LS47. The IC74LS47 is a BCD to 7-segment decoder or driver IC often used to display numerical values on a 7-segment display. The IC74LS47 typically comes in a 16-pin dual inline package. Pin 1 BCD input B. Pin 2 BCD input C. Pin 3 lamp test. Pin 4 ripple blanking output. Pin 5 ripple blanking input. Pin 6 BCD input D. Pin 7 BCD input A. Pin 8 ground. Pin 9 E output to 7-segment display. Pin 10 D output to 7-segment display. Pin 11 C output to 7-segment display. Pin 12 B output to 7-segment display. Pin 13 A output to 7-segment display. Pin 14 G output to 7-segment display. Pin 15 F output to 7-segment display. Pin 16 power supply plus 5 volt VCC. Pin 9 to pin 15 is complementary outputs. 7-segment LED display. A 7-segment LED light emitting diode display is a type of electronic display device used to represent decimal numbers. It consists of 7 individual LED segments arranged in a rectangular pattern with each segment capable of being individually turned on or off. The display has 7 segments arranged in the form of the digit 8. Each segment is labeled A, B, C, D, E, F and G and represents a specific portion of the digit. Make a connection between IC74LS90 decade counter, IC74LS47, 7-segment driver and 7-segment display. Check the pins of all ICs for missing pins like broken or damaged pins. Identify the IC74LS90, IC74LS47 with their part number printed on the ICs using magnifying lens. Identify pin number 1 from the pin details on both ICs and place it horizontally between supports on the breadboard. Connect the plus 5 volt VCC power supply to pin 5 at the synchronous decade counter IC74LS90. And pin 16 at the 7-segment driver IC74LS47 as shown in the circuit diagram. Connect the clock pulse to pin 14 at the synchronous decade counter. Connect pin 8 to IC74LS47 to ground. Connect pin 10 to IC74LS90 to ground. In the synchronous decade counter, connect pins 2, 3, 6, 7 and 10 together using jumper wire and connect them to the ground as shown in the circuit diagram. Also interconnect the pins 1 and 12 in the decade counter. Connect pin 12 of IC74LS90 to pin 7 of IC74LS47. Connect pin 9 of IC74LS90 to pin 1 of IC74LS47. Connect pin 8 of IC74LS90 to pin 2 of IC74LS47. Connect pin 11 of IC74LS90 to pin 6 of IC74LS47 as shown in the circuit diagram. Connect pins 4, 5 and 3 of the 7-segment driver IC74LS47 to the VCC power supply. In this video, we have discussed the pin details of IC7490 decade counter, IC7447, 7-segment driver and 7-segment display and how to make the connections between them. See you in part 2. Hello everyone. In the last video session, we discussed the pin details of IC7490, decade counter, IC7447, 7-segment driver and 7-segment display, how to make connections between them. To continue the session, we are going to make connections between the IC7447, 7-segment driver and 7-segment display and execute its operation. Connecting a 7-segment IC driver with a 7-segment display. Identify the pin numbers 13, 12, 11, 10, 9, 15 and 14 from the 7-segment IC driver IC74LS47 that is used to connect the output to the 7-segment display through 220 ohm resistors as shown in the circuit diagram. Connect pin 13 of IC74LS47 to pin 7 of 7-segment display for A terminal. Connect pin 12 of IC74LS47 to pin 6 of 7-segment display for B terminal. Connect pin 11 of IC74LS47 to pin 4 of 7-segment display for C terminal. Connect pin 10 of IC74LS47 to pin 2 of 7-segment display for D terminal. Connect pin 9 of IC74LS47 to pin 1 of 7-segment display for E terminal. Connect pin 15 of IC74LS47 to pin 9 of 7-segment display for F terminal. Connect pin 14 of IC74LS47 to pin 10 of 7-segment display for G terminal. Connect pins 3 and 8 in the 7-segment LED and connect to 5V power supply VCC. From the output LEDs in the digital trainer kit, choose any 4 LEDs and name it as QA, QB, QC and QD. Connect pin 12, pin 9, pin 8 and pin 11 of IC74LS90 to QA, QB, QC and QD respectively as shown in the circuit diagram. Execution. Switch on a plus 5V regulated DC power supply. Apply one clock pulse to the input at pin 14 and record the output logic levels. Observe outputs of IC74LS90. Verify the output logic levels for successive clock pulse inputs and observe the status of outputs QA, QB, QC and QD after giving each clock pulse at the input as shown in tabulation. Clock pulse 0, outputs 0, 0, 0, 0. Clock pulse 1, outputs 0, 0, 0, 1. Clock pulse 2, outputs 0, 0, 1, 0. Clock pulse 3, outputs 0, 0, 1, 1. Clock pulse 4, outputs 0, 1, 0, 0. Clock pulse 5, outputs 0, 1, 0, 1. Clock pulse 6, outputs 0, 1, 1, 0. Clock pulse 7, outputs 0, 1, 1, 1. Clock pulse 8, outputs 1, 0, 0, 0. Clock pulse 9, outputs 1, 0, 0, 1. Similarly, observe the outputs of the 7-segment display. Clock pulse 0, LED display output 0. Clock pulse 1, LED display output 1. Clock pulse 2, LED display output 2. Clock pulse 3, LED display output 3. Clock pulse 4, LED display output 4. Clock pulse 5, LED display output 5. Clock pulse 6, LED display output 6. Clock pulse 7, LED display output 7. Clock pulse 8, LED display output 8. Clock pulse 9, LED display output 9. Hope now you'll be able to construct and test synchronous decade counter. This concludes the session on how to construct and test a synchronous decade counter. Thank you.
Hello. Today we learn how to verify the truth tables of flip-flop ICs RS, D, T, JK, MSJK by connecting switches and LEDs. The video is split into two parts. Part 1 will contain the pin details, how to construct and verify RSD flip-flop, and the rest in part 2.
At the end of this video, you will be able to construct and verify with the truth table of the RS, D, T, JK and MSJK flip-flop. Let us collect all the tools, equipment and materials required to do this practical. Digital trainer kit with user manual, IC74HC00 quad NAND gate with datasheet 2 number. IC74LS10 3 input NAND gate with datasheet. IC74LS04 with datasheet. IC74LS76JK flip-flop with datasheet. Male-to-male jumper wires. Magnifying lens. First, let us discuss the flip-flops. Flip-flops are fundamental building blocks in digital electronics, providing the ability to store and manipulate binary information in sequential circuits. Flip-flops are used in various applications, including memory elements in computer systems, frequency dividers, data storage, registers, counters, and other sequential logic circuits. Let us discuss the pin details of NAND logic gate IC74HC00. This IC comes in a 14-pin dual inline package DIP and 4 independent gates. Each of the 4 NAND gates has 2 inputs A and B and 1 output Y. Pin 7 is ground. Pin 14 is plus 5 volt DC power supply. Pins 1 and 2 are inputs. Pin 3 is corresponding output. Pins 4 and 5 are inputs. Pin 6 corresponding output. Pins 9 and 10 are inputs. Pin 8 is corresponding output. Pins 13 and 12 are inputs. Pin 11 is corresponding output. We are going to use all the 4 NAND gates for today's exercise. Construction of RS, reset and set flip-flop circuit and verification of the truth table. Using the magnifying lens, identify the NAND gate IC74HC00 is printed on the top of the IC. Check that the pins of the IC are not broken or damaged. Identify pin 1 of the IC. It may have a small notch or dot to indicate pin 1. Gently insert both lines of pins of the IC into the breadboard, ensuring that each pin goes into a separate hole. Be careful not to bend the pins or force them into the holes. Make sure that the IC is correctly aligned in the right position over the breadboard in the digital trainer kit. Connect the pin number 7 to ground and pin number 14 to +5 volt supply using black and red color jumper wires respectively. Connect the pins 2 and 4 using jumper wire and connect to clock input in the digital trainer kit itself. From the input toggle switch, connect pin number 1 as set yes input to the IC. From the input toggle switch, connect pin number 5 as reset R input to the IC. Connect the pins 3 to 9, 6 to 13, 10 to 11, 12 to 8 as per the circuit diagram using jumper wires. Connect the pin 8 to the output LED Q and pin 11 to the output LED Q bar as per the circuit diagram. Verification of RS flip-flop circuit with truth table. Switch on the +5 volt DC power supply. Switch position 1 is high and position 0 is low. Apply different input to yes, set and R reset as given in the truth table and record the corresponding output levels and the status of both the LEDs. LED on means 1 and off mean 0. Input 0, 0, clock pulse, now output 0, 1, no change. Input 0, 1, clock pulse, now output 0, 1, set. Input 1, 0, clock pulse, now output 1, 0, reset. Input 1, 1, clock pulse, now output it is forbidden. Thus, we have constructed and tested the RS flip-flop using IC74HC00. Construction of D flip-flop circuit and verification of the truth table. We are going to use two numbers of NAND gate IC74HC00 for this D flip-flop. Make sure that the IC74HC00 is correctly aligned and that pin number 1 is in the right position. Gently insert the IC into the breadboard, ensuring that each pin goes into a separate hole without bending. Take the second IC74HC00, check and ensure the pins are also not broken or damaged. Identify the pin 1, align correctly and insert the IC next to the first IC74HC00 on the breadboard. This circuit requires 5 sets of NAND gates. This IC consists of only 4 gates. We have to use 2 numbers of the NAND gate ICs. Connect the pins 7 and 14 of both ICs to ground and +5 volt supply respectively. In the first IC, connect pins 1, 2 using jumper wire. Connect them to pin 1 of the next IC and then to input toggle switch as D input. Connect the pins 2, 4 of the second IC using jumper wire and connect to clock input in the trainer kit. Connect pin 3 from the first IC to pin 5 on the second IC. Connect the pins 3 to 9, 6 to 13, 10 to 11, 12 to 8 in the second IC using jumper wires. Connect the pin 8 to the output LED Q and pin 11 to the output LED Q bar as per the circuit diagram. Verification of D flip-flop circuit with truth table. Switch on the plus 5 volt DC power supply and operate the toggle switch. Apply different input to D flip-flop as given in the truth table and observe the output status of Q and Q bar LEDs. Input 0, now clock pulse Q 0, Q bar 1. Input 1, now clock pulse Q 1, Q bar 0. Thus, we have constructed D flip-flop using NAND gate, ICs and verified its functioning with truth table.
Thus, we have discussed the pin details of NAND gate IC74HC00 and constructed and verified the output of the truth table. Hello everyone. In the last session, we discussed how to construct the RSD flip-flops and verify the output with their truth tables. In continuation of that, in this session, we are going to discuss how to construct the T flip-flop, the JK flip-flop and MSJK flip-flop and to verify the output with their truth tables.
Construction of toggle or T flip-flop circuit and verification with the truth table. To construct the T flip-flop, we require a 3-input NAND gate IC74LS10 and a 2-input NAND gate IC74HC00. Identify each IC with its part number printed on it using a magnifying lens. 3-input NAND gate IC74LS10. The IC74LS10 performs the logical operation of a 3-input NAND gate. It can be part of logic circuits, arithmetic circuits and other digital systems. The IC74LS10 typically comes in a 14-pin dual inline package. From the pin diagram, pins 7 and 14 are allotted for ground negative and power supply positive respectively. This IC consists of 3 independent NAND gates, whereas pins 1, 2 and 13 are inputs and pin 12 is its output. Pins 3, 4 and 5 are inputs and pin 6 is its output. Pins 9, 10 and 11 are inputs and 8 belongs to its output. Identify pin number 1 of the IC. It's only have a small notch or dot to indicate pin number 1. Ensure that the IC74LS10 and IC74HC00 are aligned with pin number 1 correctly over the breadboard in the digital trainer kit. Gently insert both lines of pins of ICs on breadboard one after the other. Be careful not to bend the pins or force them into the holes. Connect the pins 7 and 14 to ground and plus 5 volt supply of both the ICs using jumper wires. Connect the pins 1 and 3 of IC74LS10 using jumper wire and connect them to the clock input. Connect the pins 5 and 13 using a jumper wire and connect them to the T input toggle switch.
Connect pin 6 of IC74LS10 to pin 4 of IC74HC00 and pin 12 of IC74LS10 to pin 1 of IC74HC00. Connect pins 2 to 6 and 3 to 5 of IC74HC00. Connect pins 2 of IC74LS10 to pin 6 of IC74HC00. Connect pins 4 of IC74LS10 to pin 3 of IC74HC00.
Connect the pins 3 and 6 to the 2 output LEDs Q and Q bar as shown in the circuit diagram. Switch on the 5 volt DC power supply. Toggle switch position 1 is high and 0 position is low.
Apply clock pulse and toggle inputs T as per the sequence shown in the table and observe the status of the output LEDs. Toggle input at don't care condition, clock pulse low, output LED 0 and 1, previous state. Toggle input 0, clock pulse high, output LEDs 0 and 1, no change. Toggle input 1, clock pulse high, output LEDs 1 and 0, output toggles. Thus, we have constructed and tested T flip-flop using IC74LS10 and IC74HC00.
Construction of JK flip-flop circuit and verification with the truth table. To construct the JK flip-flop, we require an IC74LS76. Let us discuss the pin details of IC74LS76. The IC74LS76 is a 16-pin master slave JK flip-flop that contains two JK flip-flops, each with J data input, K data input, CLK clock input, CLR clear input, PRE preset input, Q output and Q bar complement output with dual inline package DIP. It is widely used in a digital electronics for various applications including sequential logic circuits. Identify the code number printed on the IC for JK flip-flop using magnifying lens. Check and enter the pins of the IC and align it in the right position over the breadboard. Carefully insert both lines of pins into the breadboard in the digital trainer kit. Connect the pin number 13 to ground GND and pin number 5 to +5 volt supply VCC using jumper wires. Connect pin number 1 to the clock input. Connect the pins 4 and 16 to the input toggle switches as input J and K as per the circuit diagram. Connect the pins 2 and 3 to the input toggle switches as preset and clear as shown in the circuit diagram. Connect the pins 15 and 14 to the output LEDs as Q and Q bar respectively. Switch on the digital trainer kit. Apply different inputs J and K, preset clear and clock pulse as given in the truth table, and observe the status of output LEDs. Input JK don't care condition, preset 0, clear 0, output 1 1. Input JK don't care condition, preset 0, clear 1, output 1 0. Input JK don't care condition, preset 1, clear 0, output 0 1. Input J0, K0, preset 1, clear 1, clock pulse high, output 0 1. Input J1, K0, preset 1, clear 1, clock pulse high, output 1 0. Input J0, K1, preset 1, clear 1, clock pulse high, output 0 1. Input J1, K1, preset 1, clear 1, clock pulse high, output toggle toggle. Input JK don't care condition, preset 1, clear 1, clock pulse high, output Q bar. Thus, we have constructed and tested the JK flip-flop with their truth table using IC74LS76. Construction of a master-slave JK flip-flop circuit and verification with the truth table.
Master-slave JK flip-flops can be constructed using IC74LS76 and NOT gate IC74LS04. Identify these ICs using the part number.
Check and ensure that the code number of ICs and the pins are not damaged. Carefully insert both lines of pins into the breadboard with correct position. Connect the pins 13 and 5 of IC74LS76 to ground and +5 volt supply respectively. Connect the pins 7 and 14 to IC74LS04 to ground and +5 volt supply using jumper wires. Connect pin 1 of IC74LS76 to pin 1 of IC74LS04 and connect pin 2 of IC74LS04 to pin 6 of IC74LS76 as shown in the circuit diagram. Connect the pins 4 and 16 of IC74LS76 to the toggle input switches as J and K inputs. Connect the output of master flip-flop pin 15 to slave flip-flop pin 9 as input. Connect the output of master flip-flop pin 14 to slave flip-flop pin 12 as input. Connect pins 15 and 14 of master flip-flop to output LEDs as Q and Q bar. Connect pins 11 and 10 to two output LEDs Q and Q bar as output of MSJK flip-flops. Connect pin 1 to clock pulse. Switch on the 5 volt DC power supply. Apply clock pulse as per the sequence given in the table. Apply different inputs to J and K, MSJK as given in the truth table and verify the corresponding output levels and status of LEDs. LEDs on means 1 and off means 0. Set input JK 0 0, master output 0 1, slave output 0 1. Apply clock pulse, master output 1 0, slave output 1 0, no change. Set input JK 0 1, master output 0 1, slave output 0 1. Apply clock pulse, master master output 1 0 slave output 0 1 reset. Set input JK 1 0 master output 0 1 slave output 1 0. Apply clock pulse master output 1 0 slave output 1 0. Set input JK 1 1 master output 0 1 slave output 1 0. Apply clock pulse master output 1 0 slave output 0 1 toggles. Thus we have constructed and tested the MSJK flip-flop with their truth table using IC74LS76 and IC74LS04. Hope now you will be able to construct the RS flip-flop, D flip-flop, T flip-flop, JK flip-flop and MSJK flip-flops and verify the results with their truth table.
This concludes the session on construct the T flip-flop, the JK flip-flop and MSJK flip-flop, and to verify the output with their truth tables. Thank you. Hello everyone. Now you will learn how to construct a shift register using RSDJK flip-flop and verify the result. This video is split into two parts. Part 1 will contain how to construct a shift register and verify it in part 2.
At the end of this video, you will be able to construct a shift register using the RSDJK flip-flop and verify their results. Let us collect all the tools, equipment and materials required to do this practical. A digital trainer kit with user manual, IC74LS279 with data sheet, IC74LS379 with data sheet, IC74LS04 with data sheet, IC74LS76 with data sheet, 2 numbers. Male to male jumper wires as required. Magnifying lens. Constructions of parallel shift register using RS flip-flop IC74LS279. The 74LS279 is a quad SR flip-flop latch IC with 16 pins in a dual in-line package. Since the IC74LS279 did not have the clock input provision, the construction of the circuit is used to transfer the given input data to the parallel output. This shift register circuit requires two ICs. They are IC74LS279 and IC74LS04. Identify the code number printed on both ICs, IC74LS279 and IC74LS04 using magnifying lens. Identify the pin number 1. It may have a small notch or dot to indicate pin number 1. Make sure that the IC is correctly aligned in the right position over the breadboard in the digital trainer kit. Gently insert both lines of pins of the IC into the breadboard, ensuring that each pin goes into a separate hole. Be careful not to bend the pins or force them into the holes. Connect the pin number 8 to ground and pin number 16 to power supply plus 5 volt VCC of IC74LS279 and connect pin 7 to ground and pin 14 to VCC of IC74LS04. Connect pins 1, 5, 10 and 14 of IC74LS04 to toggle switches as A, B, C and D respectively. Connect pin 1 of IC74LS279 to pin 1 of ICLS7404. Connect pin 2 of IC74LS04 to pin 2 of IC74LS279. Likewise, connect NOT gate between R and S input for the other SR flip-flop latches as shown in the circuit diagram. Switch on the plus 5 volt power supply VCC. Apply the desired parallel input data to the data input lines A, B, C and D based on the bit width of the shift register. Check the parallel output lines Q0 to Q3 to see if they reflect the loaded data. The output should match the applied parallel input data. Parallel input 1 0 0 1, parallel output 1 0 0 1, parallel input 1 0 1 1, parallel output 1 0 1 1, parallel input 1 1 0 1, parallel output 1 1 0 1, parallel input 1 1 1 1, parallel output 1 1 1 1.
Thus, we have constructed and tested the shift register using RS flip-flop IC74LS279.
Construction of serial shift register using D flip-flop IC74LS379. This shift register requires IC74LS379 D flip-flops, a 16-pin dual inline package. IC74LS379 is designed to store 8 individual bits of data, and its operation is influenced by clock signals and data enabled signals. Identify the code number printed on IC74LS379 using a magnifying lens. Identify pin number 1 of the IC. It may have a small notch or dot to indicate a pin number 1. Make sure that the IC is correctly aligned in the right position over the breadboard in the digital trainer kit. Gently insert both lines of pins of the IC into a breadboard, ensuring that each pin goes into a separate hole. Be careful not to bend the pins or force them into the holes. Connect the pin number 8 to ground and pin number 16 to power supply plus 5 volts VCC. Connect the serial input data at pin number 4. Connect the pins 2 to 5, 7 to 12, 10 to 13 to feed the output from flip-flop 0 to the next flip-flop 1 and from flip-flop 1 to flip-flop 2 and so on. To observe the outputs, connect the pins 2QA, 7QB, 10QC and 13QD to the LED outputs in the digital trainer kit. Switch on the power supply plus 5 volt VCC. Apply logic 1 to the serial input and apply clock pulses to the CLK pin. For each clock pulse, the shift register should shift the serial input data by 1 bit. Verify that the data with the truth table. Clock pulse 0, QA 0, QB 0, QC 0, QD 0. Clock pulse 1, QA 0, QB 0, QC 0, QD 1. Clock pulse 2, QA 0, QB 0, QC 1, QD 1. Clock pulse 3, QA 0, QB 1, QC 1, QD 1. Clock pulse 4, QA 1, QB 1, QC 1, QD 1. Clock pulse 5, QA 1, QB 1, QC 1, QD 0. Clock pulse 6, QA 1, QB 1, QC 0, QD 0. Clock pulse 7, QA 1, QB 0, QC 0, QD 0.
Thus, we have constructed and tested the shift register using D flip-flop IC74LS379.
Thus, we have discussed how to construct a shift register using RS flip-flop IC74LS279 and D flip-flop IC74LS379 and verify the truth table. In the last session, we discussed how to construct a shift register using RS flip-flop IC74LS279 and a shift register using D flip-flop IC74LS379. In this session, we are going to discuss how to construct a shift register using JK flip-flop IC74LS76.
Construction of a shift register using JK flip-flop IC74LS76. This shift register circuit requires two numbers of IC74LS76 and IC74LS04. Identify the IC74LS76 and IC74LS04, the part numbers printed on the IC using magnifying lens. Identify pin 1 of the IC. It may have a small notch or dot to indicate pin 1. Gently insert the IC into the breadboard in the digital trainer kit, ensuring that each pin goes into a separate hole. Be careful not to bend the pins or force them into the holes. Connect pin 5 of IC74LS76 to plus 5 volt power supply and pin 13 of IC74LS76 to ground respectively. Interconnect both ICs using jumper wires. Connect pin 7 of IC74LS04 to ground and pin 14 of IC74LS04 to plus 5 volt power supply respectively. Connect pins 1 and 6 on both ICs 74LS76 to the clock input. Similarly, connect pin 2 on both ICs 74LS76 for preset input. Connect the serial data input to pin 4 in IC74LS76 and pin 1 in IC74LS04. Connect pin 2 of IC74LS04 to pin 16 in IC74LS76. Connect the pins 15 and 9, 14 and 12 in the first IC 74LS76. Connect the pins 11 and 10 of the first IC to the pins 4 and 16 of the second IC 74LS76 respectively. Connect the pins 15 and 9, 14 and 12 in the second IC 74LS76. Connect the pin 11 and 15 of both ICs 74LS76 to 4 output LEDs as QA, QB, QC and QD respectively, as shown in the circuit diagram. Connect pins 3 and 8 of both ICs 74LS76 to input toggle switch for clear input. Switch on the plus 5 volt DC power supply. Toggle switch in 5 volt position is logic 1 and 0 volt position is logic 0. Apply logic 0 to clear input CR. Observe the status of LEDs QA, QB, QC and QD and record the results in the table of shift registers. Apply logic 1 to clear input CR. Apply serial or data input to the circuit. Apply 1, 0, 0, 1 as serial input to the SIPO register in steps of 1 bit at a time. Give 1 clock pulse at the clock input. Observe the status of LEDs QA, QB, QC and QD and record the output logic levels. Serial input 1, clock pulse 1, output 1, 0, 0, 0. Serial input 0, clock pulse 2, output 0, 1, 0, 0. Serial input 0, clock pulse 3, output 0, 0, 1, 0. Serial input 1, clock pulse 4, output 1, 0, 0, 1. Thus, we have constructed the shift register using JK flip-flop IC74LS76. apply serial data and verify the operation with its truth table. Hope now you will be able to construct a shift register using the RS flip-flop, D flip-flop and JK flip-flop and verify their results.
This concludes this session on how to construct a shift register using RS, D, JK flip-flop and verify the result. Thank you. Hello everyone. In today's video, you will learn how to construct and test 4-bit SIPO, serial input parallel output register.
At the end of this video, you will be able to construct and test 4-bit SIPO serial input parallel output register using IC74LS95. Let us collect all the tools, equipment and materials required to do this practical. Digital trainer kit with user manual, IC74LS95 with data sheet, male-to-male jumper wires, magnifying lens. Let us discuss on SIPO, serial input and parallel output in shift registers. SIPO stands for serial in, parallel out, and it refers to a type of shift register in digital electronics. In a SIPO shift register, data is inputted serially 1 bit at a time and then shifted out in parallel all bits at once. Serial in. This indicates that the data is entered bit by bit in a serial fashion. Each bit is entered sequentially, usually on each clock pulse. Parallel out. This indicates that the data is available simultaneously at multiple outputs in parallel. The serial data, example, binary sequence 1010 is applied to the serial in input. On each clock pulse, the serial data is shifted into the first flip-flop D0, then into second D1, and so on. After 4 clock pulses, the entire serial data 1010 is loaded into the shift register. The parallel outputs Q0, Q1, Q2, Q3 represent the state of each flip-flop after the shifting process. In this example, the clock pulses triggers the shifting of the serial data, and after 4 clock pulses, the parallel output represent the binary sequence 1010. Each flip-flop stores 1 bit of the serial data. Let us discuss about the available 14-pin dual inline package IC74LS95. The IC74LS95 is a 4-bit parallel access shift register with parallel load capability. Pin 7 and 14 of IC74LS95 are allotted to ground negative and plus 5 volt power supply. Pin 1 is serial data input. Pin 2, 3, 4 and 5 are 4-bit parallel inputs. A, B, C and D respectively. Pins 13, 12, 11 and 10 are 4-bit parallel outputs. QA, QB, QC and QD respectively. Pin 6 is the mode selector with mode control input at logic inputs A is equal to, B is equal to, C is equal to, D is equal to 0. Result in QA, QB, QC and QD equal to 0, 0, 0, 0. Pins 8 and 9 for left and right shifts respectively. Construction and testing of 4-bit serial in, parallel out. Collect all the components, check them and assemble the circuit as a serial in, parallel out SIPO shift register. Identify the IC74LS95 printed on the top of IC using a magnifying lens. Identify the pin number 1 of the IC and align it in the right position. Gently insert both the lines of pins of the IC into the breadboard in the digital trainer kit. Connect the pin 7 to ground and pin 14 to plus 5 volt supply using jumper wires. Connect the pin number 9 to the clock input in the digital trainer kit. Identify the output LEDs as QA, QB, QC, QD in the digital trainer kit. Connect pin 13 to the output LED QA, connect pin 12 to the output LED QB, connect pin 11 to the output LED QC, connect pin 10 to the output LED QD in the trainer kit. Connect the mode selector pin 6 to the input toggle switch in the digital trainer kit. Connect pins 2, 3, 4 and 5 to toggle switches A, B, C and D respectively. Connect pin 1 to input toggle switch for serial input. Switch on the power supply. Apply logic 1 to mode control input and apply clock pulse and record the parallel output logic levels QA, QB, QC and QD should be 0, 0, 0, 0. Set logic 0 to mode control input and set logic 1 to serial input. Apply a clock pulse to the clock input and observe the LEDs connected to the output QA, QB, QC and QD. Serial input 1, clock pulse 1, output 1, 0, 0, 0. Serial input 1, clock pulse 2, output 1, 1, 0, 0. Serial input 1, clock pulse 3, output 1, 1, 1, 0. Serial input 1, clock pulse 4, output 1, 1, 1, 1. Now apply logic 0 to serial input and apply a clock pulse to the clock input and observe the LEDs connected to the outputs QA, QB, QC and QD. Serial input 0, clock pulse 1, output 0, 1, 1, 1. Serial input 0, clock pulse 2, output 0, 0, 1, 1. Serial input 0, clock pulse 3, output 0, 0, 0, 1. Serial input 0, clock pulse 4, output 0, 0, 0, 0. Thus, we have constructed the 4-bit SIPO register using IC74LS95, tested and verified with its truth table. Hope now you will be able to construct and serial input parallel output test 4-bit SIPO register using IC74LS95.
This concludes the session on how to construct and test 4-bit SIPO serial input parallel output register. Thank you. Hello everyone. In today's video, you will learn how to construct and test 4-bit PIPO parallel input parallel output register.
At the end of this video, you will be able to construct and test 4-bit PIPO register using IC74LS95. Let us collect all the tools, equipment and materials required to do this practical. Digital trainer kit with user manual, IC74LS95 with data sheet, male-to-male jumper wires, magnifying lens. Let us discuss on PIPO, parallel input and parallel output in shift registers. PIPO stands for parallel in, parallel out, and it refers to a type of shift register in digital electronics. In a PIPO shift register, data is entered in parallel, all bits at once, and the entire set of data is available in parallel at the outputs. Parallel in. All the data bits are entered simultaneously into the shift register, typically on the rising or falling edge of the clock signal. Parallel out. After the data has been loaded, the entire set of data available simultaneously at the outputs. Each output corresponds to one bit of the parallel data. Parallel input data 1, 0, 1, 1 is presented at D0, D1, D2 and D3. The clock triggers the parallel loading of data into the flip-flops. After the clock pulse, the data 1, 0, 1, 1 is stored in the flip-flops. Parallel out. Q0 is equal to 1, Q1 is equal to 0, Q2 is equal to 1, Q3 is equal to 1. PIPO shift registers are used when there is a need to load a set of data in parallel and have it available at the outputs without any shifting operation. Let us discuss about the IC74LS95, which is available as a 14-pin dual inline package. The IC74LS95 is a 4-bit parallel access shift register with parallel load capability. Pins 7 and 14 of IC74LS95 are allotted to ground negative and +5 volt supply respectively. Pins 2, 3, 4 and 5, A, B, C and D are 4-bit parallel inputs. Pins 13, 12, 11 and 10, QA, QB, QC and QD are 4-bit parallel outputs. Pin 6 is the mode selector with mode control input at logic 1. Parallel inputs A is equal to B is equal to C is equal to D is equal to 0. Result in QA, QB, QC and QD equal to 0, 0, 0, 0. Pins 8 and 9 are for left and right shifts respectively. Construction and testing of a 4-bit parallel in parallel out shift register using IC74LS95 PIPO. Collect all the components, check them and assemble the circuit of a 4-bit shift register on a breadboard using IC74LS95. Identify the IC74LS95 printed on the top of IC using a magnifying lens. Make sure that the IC is correctly aligned and that pin 1 is in the right position. Gently insert the IC into the breadboard in the digital trainer kit. Connect the pin number 7 to ground negative G and D and pin number 14 to +5 volt supply VCC. Connect the pin 9 to the clock input in the digital trainer kit. Identify the output LEDs as QA, QB, QC and QD in the digital trainer kit. Connect the pin 13 to output LED QA. Connect the pin 12 to output LED QP. Connect the pin 11 to output LED QC. Connect the pin 10 to output LED QD in the trainer kit. Connect the pin 2, 3, 4 and 5 to the toggle input switches in the trainer kit as A, B, C and D respectively. Connect pin 6 mode selector to input toggle switch. Switch on +5 volt DC power supply to IC74LS95. Apply logic 1 to mode control input through toggle switch. Apply a clock pulse to the clock input pin and apply 4-bit data input to parallel input pins as shown in the circuit diagram. Apply different parallel inputs and record corresponding output logic levels in the table. Input 0001 clock pulse 1, output 0001. input 0010, clock pulse 2, output 0010, input 0011, clock pulse 3, output 0011, input 0100, clock pulse 4, output 0100, input 0101, clock pulse 5, output 0101, input 0110, clock pulse 6, output 0110, input 0111, clock pulse 7, output 0111, input 1000, clock pulse 8, output 1000, input 1001, clock pulse 9, output 1001, input 1010, clock pulse 10, output 1010, input 1011, clock pulse 11, output 1011, input 1100, clock pulse 12, output 1100, input 1101, clock pulse 13, output 1101, input 1110, clock pulse 14, output 1110, input 1111, clock pulse 15, output 1111. Thus, we have constructed the 4-bit PIPO register using IC74LS95, applied different input, observed corresponding outputs and verified with the truth table. Hope now you will be able to construct and test 4-bit PIPO register using IC74LS95.
This concludes the session on how to construct and test 4-bit PIPO parallel input, parallel output register. Thank you.
Today we will discuss about